Hello everyone, I'm glad to give an introduction to our work. It's about building an integrated dataset of natural language requirements with labels of defects. Its name is PARD, which stands for Public Available Requirement Defects. And just as its name, this dataset will be public available for researchers. We ourselves also use this dataset in another paper we'll introduce in another video clip for the requirement defect detection tasks. Our work will be introduced in following parts. Firstly, I'll talk about our motivation, including the problems and related work in the research field. Secondly, I'll discuss about the basic definitions on natural language requirement defects. They are the basis of our defects. In the third part, I will show the detailed process of how we built PARD dataset, including which data we collected, how we labeled this requirement statement, and the principle of inclusion-exclusion. In the next part, I will discuss about the dataset evaluation briefly, and finally, we'll give some conclusions on our work. There are many reasons why we decided to build the PARD dataset. First of all, requirements as the helper of communication between developers and customers are usually written in natural language because natural language requirements are easy to understand, but natural language requirements could inherit defects carried by natural language. These defects might lead to serious flaws in system, so many methods and frameworks have been proposed to help developers improve natural language requirement qualities. But labeled datasets suitable for training natural language processing models in this field are still not enough. With respect to previous work, we proposed a novel pipeline for labeling requirement documents with specific attributes of defects with an open requirement dataset named PARD. This PARD dataset combines the open requirement datasets published in previous work with the public requirement documents or specifications available on the internet, and it is now available at this website. In order to apply natural language processing techniques to requirement engineering, proper collections of documents that can be used as benchmarks are necessary for training models and evaluating algorithms. And there are previous datasets like PURE pure dataset and FNRE corpus. However, there are still not as much datasets of public requirements as those in other fields of natural language processing. From the dataset used in previous research experiments, we could find that most researchers in this field now still need industrial partners to provide them with requirement data. That is to say, existing datasets are still need to be supplemented. A system requirement document in natural language is a collection of statements that provides information about required functionalities to be included in the system. So in this section, we will list different perspectives of defects we could find in those natural language requirements and give a detailed definition about them. We define under this research that a requirement statement carries the defect of ambiguity when a word or a multi-word phrase in the statement can fit two or more available meanings, and there are different types of ambiguity that might occur. An anaphoric ambiguity occurs if the text offers more than one antecedent options in the same sentence or in the previous sentence, such as the train shall send a message to the system and it provides an acknowledged message. In this system, what does it stand for, the train, the message, or the system? And a coordination ambiguity is caused by the use of coordinating conjunctions, which might lead to multiple potential interpretations. Generally, there are two types of coordination ambiguity. The first type includes those sentences that have two or more coordinating conjunctions, and the second type includes sentences that use a coordinating conjunction together with a modifier. Ambiguity also occurs whenever the truth value of the sentence cannot be decided and is associated with the usage of words without a precise semantics, such as later, as soon as possible, appropriate, etc. Many designs can benefit from the idea of atomicity. The single conceptual framework of atomicity provides a powerful way of figuring out what hides behind an action or a component composed of multiple steps. So without an atomicity, when a flaw causes a fault in the framework or system, it would be harder to detect which exactly leads to the failure. And there are two kinds of non-atomicity. The first type is from conjunction. This defect occurs when a requirement statement uses a necessary conjunction to connect two or more complete sentences. And the second type is from clause. Nested use of clauses also leads to lack of atomicity. For example, in this sentence, the using of nested clauses makes the requirement verbose and confusing. If any of the actor, the function, and the condition of a requirement statement is missing, we consider this statement as incomplete. Based on this principle, we define two types of defects that lead to incompleteness corresponding to factors that might be missing. The first kind is passive voice. The use of passive voice is a defect of completeness in requirement because it can lead to incorrect interpretations in those cases in which the passive verb is not followed by the subject that performs the action. And the second kind is missing condition. To make a requirement statement complete, each requirement expressing a condition through the if clause should have a corresponding else or otherwise clause, which is often neglected in natural language expressions. Here we summarize all the defined defect types in this table. After defining all the defects, we try to collect available requirement documents from three kinds of sources: other public available requirement dataset, documents or specifications available on the web, and the requirement mentioned in previous research. For the first and second sources, on basis of pure dataset, which contains 79 public requirements, we retrieved public requirement documents from the web with keywords like requirement documents, requirement specification, system specification, etc. We searched for links pointed to various file types, most of which are portable document formats. For the third sources, we have listed the requirement documents mentioned in papers concerning related fields in this table, which shows that most of them are from industry and not publicly available. So after retrieving these documents and filtering the ones that are just templates or duplicates from pure dataset, we renamed each of them according to the year it was finished and the system it described, so that the titles would be in a uniform format. The whole dataset is composed of 148 public requirement documents ranged from 1994 to 2019. We do not claim a full coverage of all available public requirement documents on the Internet because they are dynamic. The implement of labeling is based on the Gatewatch Bank. It is an open-source software toolkit and can serve as a framework for natural language processing, including requirement diagnosis. Building on the NLP modules available in GateTogether, we are able to propose a novel form for labeling requirement documents, and we have transformed part of the dataset into the form of text and labels corresponding to each perspectives of defects through this pipeline. Similar to most NLP pipelines, This pipeline for requirement is composed of several modules running over an input file in order. An overview of its main body is shown in the figure, and there could be alternatives for each step. The first step of tokenization breaks up the import requirement text into tokens, which can be a word, a symbol, etc. Then the splitter divides the text into sentences one by one, followed by the part-of-speech tagger. The next step is named entity recognizing, which names to identify named entities such as organizations, domain keywords, and component names. Therefore, a list of glossary terms could be an optional assistance in this module. Finally, with rules written in JavaScript, the pipeline is able to detect natural language defects mentioned above. This is an example of JavaScript for detecting ambiguity caused by coordination. Therefore, we are able to transform a whole requirement document or specification into a collection of statements and labels. It should be noticed that in the process of converting documents or of different formats into collections of plain text tuples, we only dropped the parts that are not natural language, such as photos and figures, and the not correct spelling and grammatical errors in this text. This is because we consider that these kind of errors also influence requirement quality in real life, but they are not discussed under this research, so we keep them in converted text to retain the original features of the documents we have collected. Yet we do not claim an absolute classification for natural language defects because there are many domain-specific scenarios in requirement engineering. Experts in specification fields could develop domain-related schemes for one given requirement document or specification, and we also expected related researchers interested in NLP to share those customized schemes formulated with industrial experience. Here is our principle of inclusion and exclusion. We have to clarify that the current work of labeling and transforming is limited by several factors such as the quality and the age of the document. So we established our own principle of inclusion and exclusion, and we provided the original dataset together with the labeled part. Our principle of inclusion and exclusion is that we will not label those documents which are hard to annotate in both the manual and automatic methods. In other words, annotating this kind of documents manually is difficult due to their length, while at the same time the automatic ways fails to get sufficiently accurate results because the context of those tags is too vague to be recognized. The whole finished dataset is composed of 148 documents from all walks of life. We also informally inspected each document and recorded information of some aspects. The figures shows the number of pages collected, which have a maximum of 647 pages and a minimum of 6 pages. The median is 30 while the average is 55. We also recorded how requirements were structurally expressed. The requirements expressed in a structural format such as use cases were marked with the letter S, while those written in unstructured natural language descriptions are marked with U. If mixed ways of expressing were used in a document, then we marked it with a combination. We could infer from the statistics that most of the natural language requirements in this dataset are written in an unstructured form, which means it would be quite possible to detect natural language defect within them. And at the same time, for unstructured natural language requirement, it is more difficult to detect defects and improve quality, so building dataset in this category to train new effective models and algorithms is necessary. In the evaluation part, we tested the RETA tool developed by Aurora and its collaborators on currently labeled part, which contains 1,514 requirement statements to prove the usability of our dataset. The table gives the proportion of defined types of defects in the labeled part and the result of accordance obtained by running RETA on it. It can be seen that the defect classification defined in our dataset have been fully covered, and the most common type is the defect of coordination ambiguity. The least common one is non-atomicity from clause. It shall be noted that the non-atomicity defined in RETA is not subdivided by causes, so we combine this category for comparison. Concerning the defined defect types, which are only related to words and phrases, the existing requirement review tool can achieve considerable accuracy. However, when it comes to the defects caused by complex sentence and structure, the accordance will decrease significantly. This is partly due to the vague definition of non-atomicity in existing requirement tools. Besides, difference in format and quality of public requirement documents also block automated tools from parsing long text precisely. Here is our conclusion. This paper presents part an integrated dataset for natural language requirement processing in the field of requirement engineering, together with a pipeline model to detect and review defects in requirement documents and specifications. Our dataset is currently composed of 148 documents in various formats, part of which has been ported to the form of text with defect labels through our proposed pipeline, and most of the modules and rules in this pipeline could be customized according to the needs of domain scenarios. We tested the existing reliable requirement review tool on our labeled parts, demonstrating the full coverage of defect types and the usability of the dataset. In future work, we plan to enrich the dataset with more public documents and to port the whole original dataset into collections of plain text. We also expect requirement engineering researchers and experts in industry who are interested in natural language processing to share some customized schemes or alternative module formulated with industrial experience. Thank you for watching.